Hi, I'm Leandro Facchinetti, and let's write some code together, shall we? What we have on the menu today is this. It is Bezier Curves. Why would you want to implement Bezier Curves, you may be asking? Well, we are working on this library to help you develop better looking and easier to develop, hopefully, JS effects, which are real-time audio processors in REAPER. And I have some features that I am implementing for the user interface, and I haven't really finished parsing this, but I have a selection of colors and a whole design system. Then I am also doing some things that will help you do the digital signal processing, the audio processing part of your plugin. Hopefully the plugins that will be developed with this library will have a good combination of both. They will sound good, but they will also let you see what's going on so that you can learn and also help you tune the parameters more easily. In any case, these are some digital signal processing things, algorithms that we are implementing together. Things like a biquad filter. Okay, so that's all fun and games, but what about Bezier curves? They are actually useful for both. You can use Bezier curves to draw things, and that's the typical use case. So maybe you have some kind of graphical user interface that depends on curves and that you want to draw them using Bezier curves. And you can use the thing that we are going to implement today for that. Great. But Bezier curves are also useful on the audio part of a plugin. For instance, you can have a Bezier curve to define a transfer curve. So let me see if I have an example that looks kind of okay. Yes, I think that this is kind of okay. So if you look at, for instance, just the cyan, I think, curve. Oh, Bo is here saying hi, Leandro. Hey, Bo, great to have you here. I hope you enjoy our adventure into the Bezier curves. Right, so this is an example of a Bezier curve here in cyan, and you can imagine this as a transfer curve for a compressor, for instance, or some kind of wave shaping distortion plugin. So you would look at the values in the Bezier curve, and maybe you can give the Bezier curve for the user to tweak. So you can give the control points of the Bezier curve as a way to manipulate compression, which could be interesting. So Bezier curves are great because they are the bridge between the visual and the audio portions of our library. And there are other applications for Bezier curves besides the ones I mentioned. There are, for instance, animations. You can think of this as time, and you can think of this as position. So if you want to animate something, and you don't want to necessarily just go from one position to the other linearly, if you want to have some easing so that it starts more slowly and then picks up on speed, or vice versa, you want it to start faster and then slow down as it approaches the destination, you can think of these positions over time as Bezier curves, and that's actually something that is fairly common when doing animations. So Bezier curves, useful for all kinds of things, from visualization and user interfaces to audio processing, animations. It's all over the place, it's everywhere. So let's talk a little bit about what a Bezier curve even is. Well, there are different flavors, and there is actually a whole family of Bezier curves, but we are going to concentrate in three flavors, three variations, the three most commonly used. The first, let me see if I find some drawings of these. I guess this is going to be the best we get. So the first is a linear Bezier curve. A linear Bezier curve is not really curvy, it's straight. It's not terribly interesting, but it's the foundation for the rest of them. So we are going to start with the linear Bezier curves. Then the quadratic Bezier curves are, for instance, this thing in red. And it is curvy. So in a quadratic Bezier curve, you have 2 points they are the end points of the curve. And you also have this other point, which is a control point. It's called a control point. And this is not a point in the curve itself. It's not a point in the red curve, as you can see. It's a point that is going to determine how curvy the curve will be. And then on the Wikipedia article, they talk about higher order curves, but we are only going to go to cubic. So we have linear curves, they are straight lines. Quadratic curves, they are these curves with 2 points in a line and then a control point. And then we are going to do cubic Bezier curves, which are the most common Bezier curves you're going to find out there. For instance, if you go to a drawing program like Inkscape and you go to the Bezier tool in the drawing application, for instance, draw Bezier curves and straight lines. If you just draw a curve, it is going to be a cubic Bezier curve. How can I tell that? Well, because I have 2 points in the line, they are these little points here. And then I have 2 control points that are not in the line, they're just determining how curvy the curve will be, if it is going to be almost straight, or if it is going to bend and even do some S-shaped kind of thingies. And those 2 control points plus the 2 endpoints make a cubic Bezier curve. And you may be wondering, why not go higher order? Well, because you can make paths with multiple Bezier curves. If you just take the end of a curve and start another one from there, you can draw any shape you want, but each segment is a cubic Bezier curve, and it has all these nice properties about how to change the curviness of the curve, and also nice properties when it comes to like when working with audio and whatnot. These curves have nice properties in terms of the derivatives of the curve are continuous and smooth, all these kinds of properties that are nice to have in curves. Right, so we are going to implement straight lines. We are going to implement, I don't think I can do quadratic Bezier curves in Inkscape. I may be able to, I just don't know how. In any case, we are going to do quadratic Bezier curves, and we are going to do cubic Bezier curves. Not to be confused with this path. This path is actually 2 cubic Bezier curves. And what we are going to implement more specifically is the formula that, given the endpoints, and in some cases given the endpoints and the control points, I can actually pretend that I have a quadratic Bezier curve. If I just put the 2 control points on top of one another, they become sort of the same point. And I don't think that they actually merge. If I want to move them, they still move separately, but I can pretend that this is a quadratic Bezier curve. So there you go, it's a parabola. And what we are going to implement is the formulas that, given the control points and the curve points, is going to compute the points in the curve. So you are going to give me these little points as well as this point, and I'm going to give you back the curve in black. And same for this one. You're going to give me these points as well as those points, and I'm going to return to you the points in the curve, the points in black. Useful for actually drawing the Bezier curves, because in JSFX we cannot draw Bezier curves. We can draw straight lines, but we cannot draw curvy lines. So it may be useful for actually drawing stuff on the screen. In fact, when I was doing the research for this stream, I actually found something super interesting, which is this Spline Eq. I think that's what it's called, Spline Eq, yeah. So it's actually an equalizer that allows you to draw the equalization curves using Bezier curves. You can see the little control points in the EQ curve. So fun stuff. Maybe we could implement something like this using Bezier curves. In fact, as far as I understand, the principle behind that effect is similar to the principle behind REAPER, except that here in REAPER we cannot draw with Bezier curves. They are curvy, they are smooth, lines, but we don't have control over the control points. We cannot touch the control points. We can only touch the points in the curve, and the control points are given by REAPER. As far as I can tell, you cannot get a hold of the control points. All right, so let's start with the simple linear curve, and I'm going to use the most obvious application, which is to draw this on the screen. And I'm going to do that so that we can see the Bezier curves, see that we are doing the right thing. So this is our library, and this is the demonstration effect, which is using our library. So I'm going to start by defining, how about we start by using the function, and then we try to define the function. So let's create another page. This demonstration effect has several pages for the different things in the library. So how about we put this as the first page so that when we reload the plugin, it's already there. Bezier Curves. And now we have 10 pages. And these pages are going to go from, well, we have 11 pages. We already had 10 pages. We're going to have 11 pages. And we are going to have a slider page, Bezier Curves equals 0. That's page 0. And now let's bump up. Oh, no, I made a mistake. It was supposed to be like this. Oh, no. There you go. So I bumped every other page to be 1 plus what it was before. So now the first page is the page for Bezier Curves. So let's move on to the GFX block and test for the situation where the page is this. And if I am on this page, then I am going to do this. Otherwise, I'm just going to do what the other pages were doing. And it seems like I am missing a new line on this one. Good. So how do I use this function that we are going to define? Well, Bezier curves are known as parametric curves. So you are going to have to give me the points, the coordinates for the control points, and we are going to start with the linear one. So we only have 2 control points, P0 and P1. Using the nomenclature, we are going to actually follow the formulas we are going to find in Wikipedia. So I'm actually going to put this as a comment somewhere where we define these functions. We have drawing functions. Isn't that perfect? I think I will have a section here for Bezier Curves. And I'm going to leave this as a reference. In any case, the Wikipedia article calls these points on the curve as control points as well. So P0 and P1 are control points. And in the case of a quadratic curve, we have P0 and P2 as the points in the curve. They are control points, and P1 is the control point that is not on the curve. So you can just come up with more and more control points. For instance, for the cubic Bezier, we have 4 control points, P0 up to P3. All right, okay, whatever. So we are going to have to give you the points on the curve. And so how about we start by giving this a name? Bezier Linear. And in the case of the linear, I need 2 points, P0 and P1. And I'm going to use the names I find on Wikipedia. So, actually, I'm calling the function. So I'm going to go from position 30, 30 That's x and y for p0, then x and y for p1. So how about 50, 50? And this is supposed to be a line that is diagonal like this. So 30, 30, 50, 50. It goes like this. And maybe we multiply these numbers by GFX X retina so that the curve looks the same whether you have a retina display or not. So those are the two control points. That's great. The X and Y coordinates for the two control points. But that's not all. A Bezier curve is known as a parametric curve. The parameter that we are talking about here is the time. So you can think of the time as this little dot moving across when we are drawing the curve. And this is going to be a variable that we have to define. So we need to say something like t equals 0. And then we are going to loop for a number of times. If we loop more often, so if this number here is a big number, then the curve is going to be smoother in the drawing. And if the number is small, we'll see line segments. You can see some sort of aliasing in the curve. And this is just because we are trying to draw the curve on the screen. If we were to use the Bezier curve as sort of a transfer function for a compressor or that sort of thing, then the t would be the RMS coming in, for instance. Or maybe if we are using a Bezier curve to do some wave shaping, t would be the sample coming in, and that's what so in other words, if you have a graph like this, then t is this axis, and then the formula that we are going to implement is going to be the output, or where in the y-axis you need to be. All right, so let's do this t, and when drawing the Bezier curve, I need to come up with a number of times I'm going to loop for. And I could be smart and try to detect the length of the curve or something like that. If the points in the curve are distant, then I need more iterations to actually draw something smooth. Or if the points are closer together, I will need fewer iterations. But for now, I'm just going to give 10 iterations of this. And t needs to go between 0 and 1. So I am going to take t and increment 1 over 10. In fact, to make this work, I need this to start at minus 1 over 10. So it's not necessarily the best code I have ever written, but this is going to work. It's going to take us from 0 up to 10. So think about it this way. T is going to start at minus 1 over 10. So on the first iteration, it's going to be minus 1 over 10 plus 1 over 10, which is 0. Then it's going to loop 10 times. So it's going to go from 0 over 10 up to, well, it's going to loop 10 times. So it's going to loop until 9 over 10. That is incorrect. It should loop for 11 times. We need to draw that last segment as well. And Bo is asking, any news on median averaging? Is that already on the to-do list? I think it is. Yeah, we will get there. But it's only on the sourcing situation, so yeah, we already have some stuff about moving averages. We'll get there. But no, I don't have any news. I haven't really worked on the library except for the stream, so I think that you know everything that I've done so far. All right, so 10 is going from 0 to 1 in 10 steps. And this is what the function is going to be called in this manner. Right, so let's implement this function, because as of now, if I try to load this plugin, it's going to fail, saying that I don't have that function. So let's implement that function. yes, there will be some sorting algorithms involved. And yeah, implementing sorting algorithms is always fun. It's one of those things that they teach you in university that's like rarely useful, but always fun. I think so anyway. So the arguments for the function are going to be p0x and p0y, p1x and p1y, and t. I don't think I need a new line there. I think that this is short enough. And then we can go to Wikipedia and we can find the formula for this. It's not terribly difficult. Oh, there is an issue. Yeah, there is an issue. I don't want this function to necessarily draw. So I want to have a function that is going to give me the coordinate. And that's, yeah, okay, yeah. So I want to break this apart. I don't want necessarily this function to draw. I want the function to just give me the coordinate. And then I will have another function that is able to draw. Yeah, I think I'm going to have this as like a dot draw function. Just renaming it. So the arguments are still the same and everything, but I'm going to gfx line. Did I remember correctly? Yes, so line is going to go from, well, I could not do the parametric thing with t. Oh, no, this is not gonna fly. Okay, I'm gonna have to change some things about the way that I'm using this function over here. We'll get to that in a moment. For now, let's just implement the formula for this. So the problem with the formula is that it needs to return two values. It needs to return the coordinates x and y. So how about we just make it for one axis, and then you have to call the linear Bezier interpolation on the x-axis and then the y-axis, and then you get your point. So let's say that this is just p0 and p1. This is going to be a single number. So I guess p is not a good name because p stands for point. So instead, I would just say that this is between x and y. Well, x and y are also loaded. So, well, it is p0 and p1. It's a point, but not in a two-dimensional space. It's a point in a one-dimensional space. So with that, we can finally get to implementing this. P's are capitalized. So let's look at the formula. It's not too crazy. And we can even make sense of the formula. So B, capital B, is for Bezier, given a certain time. So in this formula, it's expected that the P0 and P1 are kind of implicit, but I'm making them explicit. And then we are just taking P0. So we are taking where we started, plus the difference between where we want to go to and where we started. So if you're thinking of these as vectors, this is the vector of the difference. Or in other words, it's just the endpoint minus the start point, which is the difference, the path we need to travel times t. So how far along are we in the path we need to travel? So starting point plus a certain amount of progress towards the destination P1. So that's going to give me the linear interpolation between 2 points, unidimensional points. These points here are bidimensional points, actually. They are bold because of this. They are in 2 dimensions. And you could extrapolate this to multiple dimensions. We are probably not going to, but you can. And then you have surfaces, Bezier, not Bezier curves, but Bezier surfaces, which is super cool, but we won't get there. All right, so this is computing 1 dimension. the x-axis of, or the y-axis of a Bezier curve. So now we need to define another function, I think. I'm going to define this as an auxiliary function. So this is the kind of function you would use, for instance, if you are designing a compressor and you are interested in using a Bezier curve as transfer curve. Okay, this is going to, given an input with maybe a sample, it may be RMS that you want to smooth out, whatever the case may be, or not necessarily smooth out, but compress. Say, whatever the case may be, this is the function you use to get a hold of a point. So in that sense, we are implementing this function here that takes a point on the x-axis, takes a curve, like the cyan curve, and given any point in the x-axis, it's going to return a point in the y-axis. Great. And it's only going to do that for linear Bezier curves. So not for these curvy lines, but only for straight lines. So you could have a straight line like this. All right. So now let's have another function that is going to be the draw function. And it is going to receive all the arguments to actually draw something on the screen. Yeah, I'm going to move on with that. And in this case, I don't need t, but I will need the number of steps. So I'm more or less making an auxiliary function to abstract this, because I know that I will need something like this over and over. So how many steps do I need? And I'll also get a color and a thickness for the line, but not right now. So I'll leave myself a to-do, maybe put it on the top of the file where we'll have Bezier curves. Let's also have options for color and thickness. And then naturally we are going to call from this function that one. So how about we set gfx(x) to be p0x, and gfx(x) is this variable, it's a special variable that comes with REAPER, and it represents a cursor. So we are putting the cursor in p0x and p0y. So we're putting the cursor in p0. Now we are going to move our way to p1 over a certain amount of steps, which is a silly thing to do. We could draw a straight line between P0 and P1 right away, but we are going to do it the long and more precise way, the more Bezier way. Right, so I will need a local variable called t. And I believe I am going to do something that amounts to this, except that I am going to not do this with 10. I'm going to do this with steps. And let's think about the steps. So the steps is something like, I'm going to draw this line, but I'm going to take, let's say that I'm going to break it apart in this way. So the number of steps, is it the number of points or the number of line segments? Doesn't really matter all that much. It's going to be off by 1, but let's think about it for a moment. I think it is more correct for us to think about steps as the number of segments. That's the number of calls to the line 2 function. We are going to call the line 2 function. So the number of steps is, in this case, for instance, 3. So we have to do 3 calls to this. In other words, I'm gonna say there will be a t increment variable, and t increment is equal to 1 over the number of steps plus 1, I think. It's always difficult for me to reason about these plus 1 situations. But at least I will be able to write something like this. So now let's think about this for a moment. I want to start with 0. And I want to take 1, 2, 3 steps. Okay. What does the increment need to be? If I want to take 1, 2, 3 steps, I need to divide this line segment in 4 points. And I need this to be 0, 0.25, no, 0, 0.3, 0.6, and 1. So if steps is 3, 1, 2, 3 steps. If steps is 3, then my increment, my t, is going to be 0, 0.3, 0.6, and 1. Because this divides a third of a line and 2/3 of a line. So my increment needs to be 0.3, which is just 1 divided by steps. So no plus 1 in there. Okay, this is going to be my t increment. Is going to be 0.33. And this is going to be this over here is going to be 1 call to the drawing function, another call to the drawing function, and another call to the drawing function. So 3 calls to the drawing function. Okay, everything up to this point is making sense. So how many calls do we need to make? 3 steps, number of calls. 3 steps, 3 calls. And then the increment is going to be 1 divided by the number of steps. Okay, I think I got this. Okay. No, I think that I think there is something wrong about this. I think that this should start at 0 because we are already at P0, which is 0 in this situation here. So yeah, I think that we need to go straight to the next one. Perfect. Now I got this. Okay. So I think that the plus 1 that I needed to have here, this plus 1, was related to whatever I was doing at that point, but it's no longer relevant here. So now we draw a line to, and we can use this. This AA is for anti-aliasing. I want it to be enabled. I guess I can just use my true variable, which is 1. Yeah. It amounts to the same. It's the number 1, but this is more intention revealing. So where do we want to go to? We want to go to, on the y-axis, oh no, it's P0x and P1x And the cool thing about line 2 is that it is going to update gfx(x) and gfx(y). So the thing that we are writing here, I think, suffices. Because the next time we go around, it is going to be at gfx, x, and y, the point that we just plotted. So it's going to move along the line just fine. And then we are using the Bezier to interpolate on the x-axis and on the y-axis separately. So that's why there are two calls to Bezier Linear. Now let's revisit this because this is obviously wrong. We need to remove this loop, and now we call this with x, y, and the number of steps, so 10 steps. X, y for the origin, x, y for the destination, and 10 steps. So if we did everything right, then in REAPER we should see a straight line. Oh, we need also to set the color. Let's do a bright red. Okay, here is a line, and it has been drawn using the Bezier formulas. So fantastic. Let's review the changes. But you are giving me more to-dos than I can keep up with. The list of things to do is always growing, never shrinking. I guess that's a good thing. Right, so that is it for the linear Bezier. That's not too fantastic. It's not too interesting. Let's do a quadratic Bezier. Well, the quadratic Bezier needs 3 control points, and the way you build a quadratic Bezier is actually kind of interesting because it's based on the linear Bezier used twice. And if you're wondering why it's called quadratic and cubic and so forth, it is because of the formulas and the way that they have squares and cubes. Yep. For instance, this formula over here has a square, and then the formula for cubic will have cubes. Now we have 2 different ways to go about this. We can think of it as just implementing the formula, and that's fine. Don't be sorry, Bo. It's great to have an ever-growing list of things to do. Okay, so there are 2 ways to think about this. You can just use the explicit formula and implement it in much the same way that we implemented the other formula, but we can try to reason about what's going on. So let's use the figure on the Wikipedia article to actually reason about how Bezier curves work, which is actually kind of a cool idea. So you just use linear interpolation between P0 and P1, a linear interpolation between P1 and P2. That is going to give you these points that are called Q points on this figure. Maybe for a quadratic. And then you do a linear interpolation between Q0 and Q1. And then you keep doing that for all the t's and you end up with a curve. Great. How about a cubic Bezier curve? It's just the same idea. Linear interpolation between P0 and P1, linear interpolation between P1 and P2, linear interpolation between P2 and P3. Now you're going to get the Q points. In this case, because there are 3 lines, you get 3 Q points, Q0, Q1, Q2. Then apply the same idea, linear interpolation between Q1 and Q0 and 1, linear interpolation between Q1 and Q2. That is going to give you the R points. And then linear interpolation between R0 and R1. That's going to give you the point on the curve. And if you're wondering when you're doing the linear interpolation, the T is always the same. It's the T, for instance, in this case, 0.25 for all the linear interpolations. So from P0, P1, P2, P3, or Q1, Q2, or R1, R0, R1. It doesn't matter. In all those linear interpolations, it's the same t. So now we have a choice. We can implement this idea that I just explained using a bunch of linear interpolations. It's not a big deal, not the end of the world. Or we can use the closed formula, which is just working out the mathematics, just working out the algebra after you have, if you just substitute the formula on the next one. So if you want to think about the, where is the drawing? Come on, yeah, there we go. So if you want to think about, for instance, on the quadratic curve, if you want to define Q, you are going to call a formula, the formula we just implemented for linear interpolation. You call that formula to discover the linear interpolation between P0 and P1. When you do that, you get a Q. But you can substitute that part of the equation in the bigger equation of of the linear interpolation between Q0 and Q1. If you just work out all the terms in the formula, you will end up with the formula that is in a closed form, which has a square in that, and this formula. So we have two choices. We can either implement using this idea, and we can call the function of linear interpolation over and over to get the Q points, or we can just do it like this. The closed formula is supposed to be faster, and therefore it may be a better idea, but the other formula, it is more intuitive, so I don't know. Let's look at the number of operations. This is doing a lot of operations. This is just plugging a formula, plugging the linear interpolation formula in the quadratic one. But we can rearrange this, and then it becomes shorter. And then you can see the squares. And then there are two squares. In this one, there are two squares. Then there are three terms with multiplication. In this one, there are two. And this is actually not too bad. This formula is not too bad because it kind of resembles the linear interpolation formula where you have, it's not necessarily the origin and going up to the destination, but it's the destination and then you're adding stuff about the origin. So it's, but at least it's highlighting the symmetry with respect to P. So this formula kind of looks nice. And in terms of the number of calculations we would have to do, it is similar. It is similar. And in this one, we would have to subtract 1 minus t twice. And on this one, we only have to do it once. So I'm tempted to go with this. Yeah, I think we're going to try to use this. I think that this is probably the fastest implementation we can have. So let's move on. Yeah. Let's move on and do... Remember that we are doing this in one dimension, and then we are going to have another function that does it in 2 dimensions. And this one-dimensional one is the one you would use for like a compressor or something. So this is a quadratic one. It receives 3 points as arguments. And this is the formula on the right. So let's go ahead and implement that. P1 plus 1 minus t squared times P0 minus P1 plus the square of t times P2 minus P1. Did I get it right? P1 plus square of 1 minus t times P0 minus P1 plus the square of t times P2 minus P1. I think it looks right. So now to do the drawing, we need one more point as argument. But everything else is the same, except of course for the call. Oh, I replaced the wrong parts, didn't I? It should be quadratic draw. And over here, it should be a call to quadratic, and we need to pass along P2x and here P2y. Then on the demonstration thing, let's draw this. So for this, I'm going to go with a blue, and I need to pass one extra point. And I will try to mimic the curve that I drew here. So it is going to be 2, or even the one on Wikipedia for longevity. Yeah, so P0 and P3 are almost collinear, and then not that one, that one. P0 and P2 are almost on a straight line, not collinear, but on a straight line. And then this one is up above. So let's go to the code and try to get similar coordinates. I don't want to get from the same place, so I'm not going to go from 30, 30. I will go for from 100, 100. Then this is going to be like, let's say 300, 100. Oh, that's our P3, P2, I guess. Did I get the indices right here? Yes, starting from 0 everywhere. Great. And then over there on the formula, all right, that's right as well. Okay, so we're gonna go with blue, and from 100 and 100 to 300, 300, 100, passing by, let's say, 150 and 50. Yeah, that's going to be above. In 10 steps, why not? Okay, there is a function call that needs 3 parameters. And I forgot to rename this, quadratic. No, still wrong. The funny thing is that it's complaining about a linear call, so I don't know what's that about. Error in init. Blah, blah, blah. Oh, I think I forgot to rename one of the calls in the drawing thing here. Yeah, that one. And here is a curve, but it does not look like the one on Wikipedia. So let's reason about why that's the case. For one thing, I don't like how everything is being cropped at the top. So let's change this to be bigger numbers. No, it's still being cropped, which is unexpected for me. So maybe there is an issue with the linear interpolation already. Let's figure this out. I'm going to commit what we have because we're going to start experimenting with this. Let's add it and make this window smaller. And here on my side, and we'll look at the thing above my head. Okay. So let's find the GFX block where we are calling this. And this Okay, let's play around with these parameters. This should move things on the x-axis, and it does move things on the x-axis. And this should move things on the y-axis. But it does not. So what's up with that? Then this should change the destination on the x-axis. We should see this point moving around. And we see that. And then over there, oh, now it's a straight line, a vertical line. Good. But let's go with 200. And then this should move the point up and down. And it does move the point up and down. So really the mystery is this point. It is always 0. So that is wrong. Let's find, it's probably a typo. Let's find that typo. On the linear one. And I think we found it. And then, of course, it's going to be a typo here as well. So P0. Now, hang in there. Typo is in the wrong place. It's P0, X and Y, P1, X and Y. Then X, X, Y, Y. P0, X and Y, and P1, X and Y, and P2, X and Y. Okay, I think I got it all. Full compile reset, and there you go. Little curves, much like the Wikipedia ones. Great. Don't need this one to be in this position. Can be something like this. Then something like that. And whatever. We're probably going to like have the name of the function here with some arguments to help people figure things out. But for the time being, this is looking nice. It's a straight line, it's a curve, and it kind of looks like the straight line and curve you see on the Wikipedia article. Great. Let's do the cubic one and call it a day. So for the cubic one, it is going to be similar in spirit, except that we'll need a P3. Oh, and everything that says quadratic needs to say cubic this time. And I guess you can see how you can come up with a loop and you would be able to implement any order of Bezier curves. But I already explained why that's not necessarily desirable, so. P3, we start at P0, then we call this with P3 dot. In this case, X, in that case, Y. And then we need to come up with a formula, and I'm going to borrow the Wikipedia formula. I'm going to do it, again, we could use the linear interpolations, or we could even use the quadratic interpolations between P0, 1, and 2, and P1, 2, and 3, and then we would get R0 and R1 right away in one pass. Cool. And we could even do a loop and do this for arbitrarily many times. But I'm going to try to do the fastest thing, which is to use the closed formula, fewer multiplications and additions. So this is, let's see, we have two flavors. So this flavor here is doing the recursive call. It is not recursive, but it's calling the B function for the quadratic with 3 points, or the explicit form. So we are going to use the explicit form and see there is a cube there. Great. Take the power of 1 minus t with exponent 3 times P0 plus 3 times 1 minus t squared times t times P1 plus 3 times, I think I need to make it like this. So that the whole thing fits on a screen. One minus t times the square of t times p2 plus power of 3 of t exponent 3 times p3. Okay, let's review this. Take the cube of 1 minus t times p0 plus 3 times 1 minus t squared times t times p1 plus 3 1 minus t times the square of t times p2 plus t cubed times 3. Lovely. And then we already did everything else here on the cubic draw function. So that's good. We can move on to use it. And on this one, oh, I think I'll let this be green and this be blue. So we have red, green, blue situation going. But we'll need a fourth point. So let's go to the Wikipedia article again and try to draw something similar to that. So P0 is, let's say, let's say 100 and 300. Then P1 is a little bit before that, so let's say 90, but above, so let's say 250. Then P2 is almost the same y, but it is a bigger x. So let's go to 250 on that one. And then finally P3 is the same height as the first point, but it is to the right. So 310 steps. There you go. Let's save. Let's reload, full compile, reset. And there is a problem with 386. That's the line with the issue. Well, we need to call the cubic version of that, okay? And there you have it. Now for this one, I think we need more steps to make it smooth. So how about we change this number to 20? And it's better. It's not perfect. It's not perfectly smooth. But it is a cubic Bezier curve implemented from scratch with our bare hands. Great stuff. There's still more stuff we could do with this, but this is good enough for now. So thank you very much for watching. Thank you for supporting me on PayPal and Patreon, and for subscribing to the channel, for just being here and watching. Thank you both for being active on the chat, and everyone else who was just silent but watching, or maybe watching this in the future. It's great to have you here, and I see you tomorrow for something else. I'm probably going to do the colors. I'm going to port the colors code here. So lots of finding variables, renaming variables, tuning the naming conventions and whatnot. So I see you tomorrow for that. Bye.